Hello, welcome to this video on statistics and analysis. In this first session, we are going to cover a few topics, namely the definition of probability, right? What is called the sample space. And because of the definition of probability, we'll also talk about counting and how to count. Okay, no big theory, just cut to the chase, directly deal with the core definition and understand it via a few simple examples, but even complex examples are built from simple examples. So we should benefit from analyzing and understanding totally very basic, simple examples, right? So first thing first is the notion of probability. And it is very simply defined by a ratio of the count of our wanted interested set of items A. So we can write it as count of A over the count of what we call the universal set. So I just put a little tail here just to distinguish the universal set from the letter U and union symbol. All right, so we talk about set, right? Set means a collection without ordering. And right now in front of your class, there may be a set of students because the students can choose to sit anywhere in the classroom. And your set of stationery in your bag, right? So that's just jumbled up in any order. So that's the idea of a set. Unique items, right, that count. So the probability of the set A or event A and is defined by, right? Is defined by the ratio of counting the items in A and counting the items in the universal set that naturally encompasses A. So A is always a subset of U. So to put it simply, we can, of course, illustrate with counting, right? So we can have 5 balls, let's say. We can call this A, right? How I encircle it, whether it's a rigid rectangle or a, an odd shape kind of a bag, encircling it doesn't really matter, as you understand, right? So we can do an oval or we can do a nice square, but it doesn't really matter. So it's like B includes, right, or is defining these 2 items as B. And then of course C, we can have this. That is totally not touching, not related to, has no interaction with A and B at all. Okay, and of course we can call this whole thing the universal set. All right, and so this is everything inside the universe. Of course, the idea of universe is to say that the whole context and scheme of things that we are interested in calculating, in counting. Outside the U, of course, we can have many balls, but so long as they are, belonging to other people, not involved in our discussion here, etc., unrelated, then we don't care. So long as we talk about probability, then the universe is just here. And within the universe, we see only 3 events that we are interested in. Okay, so and that is A, B, and C. And they are made up of entities. Right now, we just draw it as balls, right? The balls have no colors, have no other ways to distinguish them, have no labels, and our grouping is like this. Yeah, and of course, you can also find such situation in other applications where the balls are labeled A, and B, A and B, and then this is B and this is C and C, right? So you don't need boundaries to define the grouping under C. It can be actual physical boundary. Don't get out of this place, then you are considered C. Or you can move anywhere. The ball can be physically anywhere. You can, bounce around and move around, but you're labeled C. The C IC card, the passport is attached to the ball, right? So if the ball is caught, who are you? And then you show your IC, I'm C, or I'm A, or I'm B, right? So it can be also identity grouping. Okay, so the concept of grouping need not be physical, but can be tagged, right, or virtual in that sense. Just ID with the ball. That's all. Yeah? So now we ask a few simple questions. Yeah, we can say, what is the probability of A? So we say count of A, right? So count of A over count of the universal set. Typically in this calculation, counting the universal set is very simple because it doesn't change and it's often easiest because you don't care about boundary and labels and whatnot. You just go ahead and count all the unique balls. 1, 2, 3, 4, 5. So the denominator is 5. And for A, in this case, is very simple. We just look at whatever balls is in A. Actually, not so simple because here, is this A or AB or B? Well, the way we try to show here is to say that this ball has two kind of memberships. It's like, are you a MasterCard holder or a Visa card holder? Well, I'm both, right? I can show both cards. So are you A or are you B? I'm both. So if I say A guys come here, then you come here, right? So I count. So 1, 2, so 2. Is that clear? Right. So very simple. I'm done. So what is this 205? What does it mean, right? I can count, you can score the mark, but what does it mean? Well, it just means that if I close my eyes and randomly point at one ball, all right, so long as I don't look at it, that's the Schrodinger's cat dilemma, right? So long as I don't look at it, I have a 2/5 chance of pointing at a ball. That's the whole idea. Another way to talk about the same interpretation is that if I randomly, it has to be random. It cannot be very biased, like guided by someone who is eyeing the balls, right? So it has to be random. If I randomly shoot 5 arrows, I can pretty comfortably say around 2 arrows will end up hitting the 2 balls. Right? Of course, all 5 arrows have to hit some balls. Yeah. Or if I shoot 1,000 arrows, right? And I don't know how many actually hit the balls. Some don't, right? Some fall into empty spaces. So let's say, right, 10 arrows end up hitting the balls. The rest all missed, all stuck in the gaps, right? So of all the arrows that are hitting balls, I can say 2/5 of those arrows that hit the balls will be A. So you see, there are just a few ways, right, to interpret that. And one thing you should keep in mind to do well in your tests and exams and quizzes is that probability, right, is equal to proportion, at least in terms of calculation, is equal to percentage, right? So if I say out of 10 arrows that hit the balls, the percentage of arrows hitting the A balls will be 40%. See, because it's 2/5. Or I can say the proportion. Probability is a very virtual concept, right? But proportion is a very real concept. Yeah. And the idea is once the 10 arrows have hit the balls randomly, the proportion of arrows hitting the A balls will be 2/5. You see, so that proportion idea and percentage idea is kind of equated with probability. And I kind of took it for granted, but of many semesters of talking to students, I realized a lot of students cannot get this idea. So that when test questions come out, they say 2/5 of the arrows hit the A balls. What's the probability of hitting the A ball? And they may not be able to answer. I hope that's not you, right? But I thought that was serious enough for me to point this out, right? So just treat them as the same. in terms of calculation. But in uh, I'm always getting into a bit philosophical because probability does get into this virtual land, right, where it's about the future, it's about the unknown. Huh? So this is actually about the unknown, about uncertainty, right, and typically about the future because nobody knows the future, and that's why it's unknown. But even if it's a present, for example, what's the probability of a penguin being killed at the North Pole? Well, it's happening now. You and I are not there, but it's happening now, right? We can agree. We don't see doesn't mean it doesn't happen, but we don't know. That's unknown to us, right? But there's a probability. That's not zero because you'll be eaten by whales, by orca, by polar bears, right? So there's a non-zero chance. But what's that chance? What's that probability? And that's expressing that unknown. And hopefully it's not near 99%, right? But that expresses unknown situation or future situation. Proportion and percentage, they tend to, in terms of our common usage of these words in language, typically refer to known, right? Shown or factual. It means after the fact, right? Uh, and because of that, because it's factual, it's usually associated with present or more generally the past, right? Because it's done, it's been found, it's been counted. I saw the proportion of 40%, right? So that's just a more subtle appreciation of the fine differences between the words, right? When it comes to tests and quizzes, there's no time to talk about philosophy, yeah? So just go ahead and equate the numbers because that's how the question will be phrased to see if you can use this equation. The fact that percentage is just probability, percentage 40% in the past means 40% chance in the future. That kind of connection to test you whether you can do the math or not. Yeah. And so once we have covered this far, it's good time to talk about sample space, right? So just to extend this example a little bit further before we jump into the sample space, is that just now I talked about this circling, right? Just to show membership, but this can also be done as a Visa or MasterCard labeling. So if I call this AB ball, if I call this A ball, right, and this is labeled, it doesn't matter whether the ball here that I draw here is shown as a big ball or small ball, right? But it's the label that matters. And now there's no boundary, and we still have an equivalent universal set. And now the probability of event B happening, that means if I close my eyes and randomly pick a ball, what's the chance that it is a B ball? Well, it's the same, right? 1, 2, there are 2 B balls because I asked this ball, are you A or are you B? Well, it will say I'm A, right? So that's why. So you can think of this as blood type as well, right? Are you of the blood type A or having the element or the whatever it is, right? The blood cell A. Well, if I'm AB, then I also have that blood cell A, so yes, right? So 2 out of 5. And for B, same thing here, so 2 out of 5. And finally, for if I randomly pick a guy, let's say C is O, I don't want to use O because it looks like 0. So if I randomly pick a person from the street, what's the chance that the person has type O? Well, in this case, also, unfortunately, 2. 2 out of 1, 2, 1, 2, 3, 4, 5. 5. Okay. So far, so good, right? So that's quite straightforward. Now, if I were to now, extend the idea and talk about sample space. Sample space will be the set of all events that can ever happen when we perform a probability or statistical experiment. So set of all events. And being a set means the events will be unique automatically. That means we don't double count them. We just have the label. So for example, here we see many A's, but the event is A, right? So it's just A. Here we have multiple B's, multiple C's, but it is just B and C. So set of all events. So therefore, in this example, if we just, these two pictures are basically equivalent. So if we use the same example here, then the idea is basically to say that it is A and B and C. And you can just put as C and B and A and C, A, B, doesn't matter because it's set. So the order doesn't matter. Now, the one way to sort of remember sample space more correctly is to say, is to remember that the sample space is on the x-axis. Okay, the sample space is on the x-axis. And what about the y-axis? Well, that's the best part of today, right? That is the probability. So when you see sample space, number one, it goes to the x-axis. Number two, right? The y-axis immediately has to be the probability, or sometimes we abuse it a little bit and write it as frequency. And in that case, then it becomes a histogram. So not surprisingly, in probability chapters and even quizzes, you will see histograms being shown. Hey, yeah, be alert, because when you see histograms, and because the vertical bars are frequencies, they are basically the counts, right? Frequencies are counts, and these are frequencies. So another way to say is the frequency of A divided by the total frequency, right? So the total frequency can be an odd, even integer, can be an integer larger than 1. So 101, 113, 125, and whatnot, right? It can be an integer that has nothing special. It doesn't have to add up to 100 or whatnot, right? But probability, once you divide by the universal set, right, it has to add up to 100. It has to add up to 1, right? So because it has to divide by the universal set to give you a 1. So here we will have the sample space, for example, A and B and C. And here we will have the frequency. Sometimes we put it as frequency, but more correctly, we write it as probability. But you see that when you present it as financial charts, you know, in public listed companies, end of year reports and all this, you write decimal places probabilities is very hard for general public to understand, right? So we typically will then show as frequency. But what is necessary here for you is to appreciate, right, that the sample space refer to the x-axis and the y-axis is the frequency of occurrence, or once you divide by total frequency, that's the probability. Okay, so when we need to calculate, operate on these sets, these events, for example, more complicated statements like P of A intersect B, right? What's the probability of a ball being both A and B? So you can read this intersection as and interchangeably, right? In case you forgot your high school learning, the intersection operator, like an inverted U, right, that's treated as the overlap, a region, right? In other words, they are asking, what's the overlap region of A and B? And it could be nothing. If there's nothing, then there's a count of 0, right? And word-wise, you can think of this as and, right? How many balls are there in A and B? Now, so translating this into our count formula, it just simply becomes count of those number of balls in A and B right, over the count of universal set. Now, the denominator is not so interesting, but of course, it's very important to make it a decimal number smaller than 1. So now we count, right? So the top part is where we want to spend sometimes a lot of times. But in this case, very simple. We look at the picture here, whichever one you want to look at, whichever is easier. We can, if you're a robot, then we literally inspect every ball. Are you A and B? Are you A and B, right? But then, of course, our eyes quickly bring us to the region of intersection between A and B. And if this region has nothing, then it is okay. We will replace the count as 0 because we counted nothing. Over here, we did count a 1. So here we have 1 over a 5. All right. So when you can see this, it is good. It is easy because we just directly count. We just directly count. The difficulty comes when we cannot see this picture. When we cannot see this picture. I'll show you an example after this following sub-example. So we can also look at the other way. What is the probability if I randomly pick a ball that the ball is either in A or B? Right, I want to say that. That means I close my eyes, I just randomly pick a ball, and the ball happens to be anywhere in this region. Anywhere in this region. Yeah. So I want to say it in terms of operator without the tail, without the right tail here on the ground. So this is the union operator. And you can treat this union, read it as or, A or B. Now this is a logical or. That means our set or, our notion of this or that or both. Now this or that or both. Because if you ask, do you want coffee or tea? Then the person say coffee and tea. It will never happen, right? I mean, this is like either coffee or tea, right? So that is what we call the exclusive or. You pick either one. You pick either one. But here this or is, if you like, call it the inclusive or. That is A or B or both. A or B or both. So we count, right? Because that just goes into A or B, and then count off the universal set. Yeah. So we look around the map here and see how many balls are A, 1, 2, or B, 3. Right. Or another way is just to look at the big circle here, big region here, all right, and then count whatever ball is encircled by this new plastic bag. Oh, okay, so 1, 2, and 3, right? So we count 3 and over 5, finish. So if you have a picture or a number, right? So like this, for example, yet another way to show this is A has got a count of 2, right? A and B has got a count of 1, B has got a count of 2, C has got a count of 2, right? So if you're shown this table without a map, a diagram, but it's the same. I'm just moving this out so that I don't block. Right, it's the same, right? It's conveying the same concept as the picture, and you need to then draw the picture first, because this A and B may be hard, a bit abstract in the mind. So you want to like render it out to see that, oh, it just means the same idea here like this, right? So you have to, it should give you back the same map. That means this written very programmatic kind of text here is giving exactly the same information as this picture and also the same information as this picture. So I hope you can see the equivalence of all three. And you need to be capable of understanding these three, right, ways of presentation to you, right? So this is the frequency, so that you can answer questions in the tests and quizzes easily, whatever. Sometimes you may know the probability concept. Sometimes you may know the formulas. You remember by heart. You don't even have to look at the formula sheet. But, right, words like these totally turn your head upside down because you didn't realize that, wow, where is the input probability? I keep looking for probability and there is none, right? Because the text in the tests gives this percentage. use the percentage as the probability. Or the data, right? In the test, they gave the frequency in table form like this. And then because you kind of couldn't map this understanding, you cannot apply your knowledge at the bottom, right? Then you cannot calculate. So please have a look at in this simple example, right? And then you should be able to go from there. Now let's look at the case when we have to use some probability algebra, right? And what's that about? So we, especially for A union B, yeah, in this case, A and B, we basically need this kind of information, explicitly telling us how many overlaps are there inside the overlapping region. If no one tells us this information, if no one shows us this one more occurrence in the overlap region, if no one tells us how many soldiers are there in this demilitarized zone, right, something like that, we won't know. So that's like new information that we need to know. But once given this, we can be asked, what's the probability of A union B, right? So you can be given this input and asked to calculate P of A union B, because there's a tricky part here. So we write this again, P of A union B. So when we did this, we did do a count, right? We can say that count of A alone. Okay, let me count those that are A. 1, 2, strictly, right? Plus count of B alone. Which are the balls that are B? Or I task two of my assistants. Go and count those that are A, go and count those that are B. And the two assistants come back, right? They will tell us faithfully, this is 2, this is 2. Then of course you can see why that is a problem, because there's an overlap, isn't it? Yeah. So we then need to say minus the count of those that are in the A union, A intersect B in the overlap region, one time. Actually, you might want to say 1 times this, because we had these two assistants, they clearly have double counted, right? So assistant 1 go and count this A and B 1 time. Assistant 2 also goes there and counts the A and B 1 time. So you just need to minus 1 copy of A intersect B, correct or not? Yeah. So counting is so much easier to see, so much easier to see. And once we did this correct counting, right, based on C of A union B, our intention is to count those at A union B. But suppose we split it apart like this. We have 2 assistants, and remember, A and B could be 2 districts in Singapore, right? Ang Mo Kio and Toa Payoh. Go and count the number of residents. Right now, yeah? Or another is Toa Payoh and Bishan, right? Go and count the number of residents, yeah? So something like that. So, well, it's massive, right? So we need 2 assistants, and they are going to report that whatever it is, like 10,000. This one is 9,000. And we know there's an overlap, so we need to minus off the overlapping region, those in Toa Payoh, for example. Okay, so this we understand the logic going from here to here. And of course, the denominator, no change, because that's the easiest in any difficult calculation. Is also the easiest. So just get the denominator first, so that you know the numerator cannot exceed the denominator. If the numerator exceeds, then you're wrong in the numerator. Okay, so up to here, we see that we can just do, what is it? So 2, right? So 2 plus 2, another 2, minus the C of count of A and B. Count of A and B can be given here. If we are given table form, we will say count of A alone, count of B alone, minus count of A and B. Right now, yeah, so it's totally very clear, because there's a trickery there. Did you minus count of A and B or not? Yeah, so we minus 1 and over 5. So here we get back a 3 over 5. And we know that it is correct because we actually did this 1 by 1 manually. So it has to be correct, right? Don't need complicated mathematics. So we know it is 3 over 5. Now, if you do the direct algebra, so that you can just do the direct bracketing here, divide by C of U, and do this divide by C of U, and do this divide by C of U, you realize that each of these 3 terms is themselves a probability definition, right? Because count of A over C of U is just P of A. Count of B over C of U is just probability of B, and minus count of A and B over C of U. That's probability of A intersects B. See? Yeah. So if you have a map or you have a frequency table, please do the counting. That's my suggestion. Okay? Please do the counting. Some of you will like to convert this to probability, then you apply this. I say good luck. You just confuse yourself. Because when I count, I'm very clear. It's like Sesame Street, right? You can just count 1, 2, 3, 4, 5, finish. Very, very clear. Probability, very subtle, because our brains are not very good with 0.1 compared with 0.01. You hear me correct? Yeah? I've seen students writing, since the probability of 0.09 is smaller than 0.05, therefore we reject the hypothesis and whatnot. You will learn later on, but then 0.09 is smaller than 0.05. Are you sure? That's what I saw in the exam papers multiple times, right? So our brains are not very good. Not very good. I myself might just had done that. I have no idea, but then it is the decimal places are just not for our brains, but counting, yes. So this is still useful, all right? This algebra operation is still useful when they give you yet another kind of table where they say the universal set, right, or the distribution. Here we change it to a new word called distribution, something we will talk about more in the next few sessions, where they say A is 2/5, right, 0.4. The P of A and B is 0.2, right? P of B is 0.4 and P of C is 0.4. Now, look, this table looks a lot more like professional, looks a lot more like the prim and proper hard test questions, right? Because they give you now probabilities. And that's where our brains start to like become very foggy, cannot see the truth anymore. When actually these are just converted to divided by 5. Why 5? Why is it 5? Not the Wi-Fi. This is why is it divided by 5? Well, because in the test question setter's mind, they were looking at their own picture for their own easy understanding. You understand? Right. So they understood that, correct. How come they don't add up? A plus B plus C. Hey, it doesn't add up to 100, 1.0. Something is wrong. No, nothing is wrong. They know nothing is wrong, because they're looking at this picture, right? So when they make this picture a lot harder to understand like this, for them it's easy because they know everything. The 5, the magic number 5, right? But you don't see the 5 here. Notice something? All these add up to not 1. So there's a bit of a not a problem, but a hidden tricky part somewhere, right? Number 2 is you don't see the number 5 there. Then you say, well, very simple. Then I multiply by 5 or multiply by 10. How do you know which number to multiply? How? How do you know? You have no idea. I have no idea too. Then I multiply by as large as it is to make it an integer. No, need not be correct. Right? So what should you do? And what happens if this is 4, 1, 2, 3? Then you go to like draw 4,123 balls. Is it? Right? So very tough. This is when you have to use this formula. This is the tough nut case. Then no choice. We grudgingly use the algebraic formula. Because you see, here it is minusing probability. I don't know what it means by minusing probability. Probability, it's like how to minus, right? But as a number, you can minus if the information is given to you. So here, if you use the information on top, then it is 0.4, right? Plus 0.4, yeah, minus 0.2. So that's 0.8 minus 0.2, 0.6, which is exactly 3/5. Of course, it is exactly because you see the original hidden information. That's what makes it tough, right? So in this case, when you are presented with a probability table, distribution, as we call it, like this, right? Then we better be careful, and we have no choice, right? We cannot times back a denominator because we don't have a good selection of a denominator. We have no ground to choose a nice number to make it work. So no choice, we just directly work with the algebra, and that's a lot easier. Now, so choose the way that is easiest to tackle the input information. That's what I want to share with you. Yeah. Now, just a bit of additional elaboration on the counting, right? So what happens when the numbers get big, right? So this ball is what we can understand as discrete sample space. So one piece, two piece, three piece, discrete sample space. So sample space can kind of break up into discrete or continuous. Right, discrete sample space will be as what we saw, A, B, and C, 1, 3, 7. Okay, it doesn't have to be as in sequential running number. Typically, students will say this is a integer, but no, not necessarily. I can also have 1.33, 2.41, and 5. I can also have this. Okay, that's still discrete sample space. That means if I randomly pick a number, it has to be 1.33, 2.41, or 5. No other ways, no other choice. Yeah, so that's just think of it as three of your friends, right? They have different heights. Well, not 5 meters, but 1.6, 1.7, 1.8 meters, right? So if you randomly pick one of your three friends, it will have to be 1.6, 1.7, or 1.8. There's no in between, right? So that's also a discrete sample space. Continuous sample space will be, of course, all the number ranges. Example from 0 to 99. That means all the numbers from 0, 0.1, 0.001, 1, 1.3, everything, number range. So we typically use the square bracket to say 0 is also included. 99 is also included. Okay. If we don't want 99, if we don't want 0, then we say 0. We use a round bracket. But this is just simple notation to distinguish the differences. What are some of these examples here? So let me just give a few more continuous examples. So it can be 1 to 20, but I don't want 20 like this. No? So that's another thing. All right. So what are some of the applications? So obviously the discrete case, we have dice, right? We have what is it? What else do we have? Poker cards, right? Well, those are more for games. Maybe your favorite exercise, right? There's a lot, maybe 50, maybe 100, but it cannot be infinity right now. So it has to end somewhere. And if you like badminton and table tennis, there's no in between. So it has to be discrete, one by one, right? And for that matter, favorite color, favorite subject, and the list goes on. Okay. Whereas for continuous, I will just give you the general sense, and then I'll explain why. So typically, anything that deals with time, money, all right, time, money, physical quantity, like distance, physics, right? Time, distance, energy, right? And you can just find out from your physics friends, right? And the derivations from that, okay? And derivatives. That means measurements that are derived from these. For example, the ratio, distance divided by time. So speed, right? Acceleration, area, because it's distance squared, right? Distance squared. So area for that matter, volume, and so on. We energy, kilowatt, kilowatt per hour, and so on and so forth. Right? So dollars per hour, payment rate. So they are all derivations from the basic physical measurements. We, at least in statistics and probability, we are modeling those physical quantities in this real life continuum. So we tend to use continuous measurements. Now, why I say this, isn't that obvious? But no, because the student, tend to be correctly understanding some of these objections, because you might say, hey, but then if I look at the clock, right? You say time is continuous. If I look at the digital clock, I only see 2:58, 2:59. Let's say there's no seconds, right? 3 o'clock, 3:01. I don't see in between. So that means time is discrete, isn't it? And you're not wrong. You're not wrong, because if I set the test question and say, using a digital clock that shows only hour and minutes, list down the sample space, or how many, or what's the size of the sample space. In other words, count the number of distinct occurrences in the sample space. So you have 60, then times 12, right? Or something like 720. Yeah. So that is the very specific description of this example, a digital clock without seconds label. Then yes. Right. But then if they say, John is trying to model his work hours spent, at his office, because there are times when he spent 8 hours and 20 minutes. There are times he went in the morning for 4 hours of meeting and then he goes home. And boss lets him go home, right? So all these, he wants to have a model of his time spent at the office. Okay, fine. Now what? Now should we use a discrete sample space or continuous sample space? Okay, then you must, the question is not to ask, did he use an analog watch or digital watch, right? That's not your question, right? So in this question, then you will have to automatically use continuous, yeah? Okay, so because it involves time, duration, yeah? And if it involves his salary, because he's paid by hour, right? So then it's $1 per hour, then it is still continuous, and so on and so forth. So anything that has got to do with this, which will include a big set, because if you include the derivatives, the integrals, the ratios, right, then it will have a lot more nouns around these measurements, right? All the measurements, speed, acceleration, power, wattage, payment rates, and losses per hour, and anything that deals with money and time. In business, there's a lot of measurements that deal with that. So a lot of times we use continuous, but just don't forget that discrete sample space is a lot easier to type out in the test. That you don't underestimate, because it's not a trivial concept when we type questions and set tests for you guys to do, right? We don't want to go about describing in a very complex, difficult way that will also take us a long time to write down the question before we can ask the question. So for discrete sample space, if I show you an example like this, which of the following is a discrete sample space, right? So it's a lot easier to write, or circle the discrete sample space. So then you just circle. It's a lot easier to write down. So discrete sample space questions tend to also happen because of its ease of being described on paper. Okay, so that much for the probability and sample space. Next, I want to talk briefly about the way to count, because we talk about counting, right? And there may be questions involving most of the time discrete sample space, dice, poker cards. Okay, so if that's the case, then we want to have a way that is going to systematically count correctly and quickly, rather than for us to think or even write down, 1, 2, 3, or ace, queen, jack, or whatnot, and then we might miss some of those combinations and stuff that we couldn't think of at that moment in time. Okay? So I want to talk about counting. So to do the counting, I'm just trying to think of which way to present it the best. Okay, maybe another space. Okay, so let me just include here first. The counting, right, will involve permutations and combinations. So these are basically the fundamental ways that we learn actually in secondary high schools to systematically count some of these encounters and situations very quickly and very correctly, right? Without having to list them all out. Sometimes the listing can go to thousands and thousands, so there's no way to do it in a very productive manner, except when we apply the formula. All right, so in what follows is, of course, optional to you. You can think of whether to continue hearing, or you can just stop the video right here, right? Okay, so but then I think from what I have encountered, it's very odd or very hard to do probability to solve problems, to solve easy daily encounter kind of problems without knowing or without applying permutations and combinations. It's just hard, right? Like solving problems involving dice and poker cards. It is just rather uneasy. Even if you get an answer, you will get an answer, but you're not sure whether it's right or wrong. So that is the uneasiness that I'm talking about, right? Because you thought you have counted, but then you're not sure you have counted all of them. That's why I think since we already have the math here, already done up by the mathematicians, so just pick up this tool and apply it. It's really very helpful because it is the fundamental activity in probability to be able to count correctly. So if you cannot count quickly, if you cannot count correctly, how do you expect yourself to do probability right now? Yeah, so that's my proposal and my reason why you should not stop your video here. Okay, so I'm going to flip over the page to have a bit more space to talk about.